Hello everyone, welcome back to my YouTube channel. So for today's Power Electronics Laboratory episode, we will be having the experiment number 1 or the introduction to circuit modeling. Again, this is Ricky S. Casabana from ECE31 and I hope you will be learning something for today. So for our objectives, we aim to familiarize with the PSpice simulation software. Second, we aim to capture diagram of switching circuits. And lastly, to model the switch based on the set parameters. So later on, we will be exploring with the PSpice software and we will be explaining the principles behind the switching circuits. So just stay tuned and keep on watching to learn more about power electronics. Following our experiments procedure, we have to open the ORCAD capture or the PSpice software from our computer, and then we have to create a new project. And then we have to choose analog or mixed AD, and then we have to name our experiment Experiment1. And then of course, do not forget to select folder location where you will save your file. So here in my case, I want it to be organized, so I will be saving it in PowerLX. So we will be saving it in PowerLX lab here. So don't forget. Okay. And then click OK. Okay. And then click OK. And then after that, we have to click Create a Blank Project and press OK. And then there will be a pop-up on our screen wherein it will be directed to our schematic blank area here. So this will be the area where we will be creating our circuit. Now, this time, we will be creating our circuit. So to construct our circuit, we will be placing our first component, which is our pulse voltage source. So let's go here in source and then voltage source, and then we will be needing a pulse voltage source. So let's connect it here and then press escape. And then for our next component, we will be placing another component, and then let's search for S-break. Okay, so S-break, and then it is a voltage controlled switch breakout device. So let's place it here. So double click and then let's drag it here. And then we need to press escape, and then after that we will be needing another voltage source, but this time this is a DC voltage source. So we will be placing a DC voltage source on our circuit. And lastly, okay, press escape. And lastly, let's place another component, which is our resistor. So let's just rotate our resistor in accordance to the requirement of the circuit. And then, importantly, we have to take note of this arrangement of our circuit as well as the circuit parameters for each of the PSpice component. So here, this will be our pulse voltage source, and then this will be our S-break, and this will be our resistor, and this will be our DC voltage source with the 24 volts value, our resistor with 2 ohms, and with V pulsed with this parameter. So you have to take note of that for our schematic and the PSpice software. Now, going back to our circuit, so let's just exit this one and let's zoom in our circuit. And you have to take note of this. In order for us to have a working circuit, it is really important to make a proper grounding on our circuit. So we have to place ground. So you have to make sure that our ground has a 0 label on it, meaning it is grounded. So we have to place it under our resistor, and then let's press escape. And then we have to connect all of our circuit components, starting from our resistor, and then our DC voltage source here, and then our S-break here, taking note of the positive and negative terminals of our S-break, and then our DC voltage here. Okay, so let's just place it properly, and then the connection of our DC voltage to our S-break, and then for our next connection, we will be connecting it to our voltage supply, which is a pulse voltage supply, and then the negative of the S-break to the negative of our pulse voltage source. So this will be our circuit for our experiment number 1. So now, for our parameters, let's edit the value of V1, which will be 0 in accordance to what I've showed you a while ago. And then V2 will be 5. And then TD will be 0. Okay. And then Now, to make sure that our circuit simulation will be working properly, we have to take note that there should be no floating node on our circuit. So we have to ground as well our pulse voltage source here. So let's put some ground here, and then let's connect it through a wire. And then this will enable us to make sure that our circuit will be functioning well. Now we will have our simulation profile to run the circuit. So you just have to click PSpice, and then go to new simulation profile, and then we will be naming our simulation profile Experiment1. So let's create, and then as you can see, there will be in our software wherein the run button here for our simulation will be working already. And again, there will be a pop-up here which will allow us to edit our simulation settings, which in accordance in our own preference or the project or the circuit requirements. To edit our simulation settings, we have to set our analysis type to time domain, okay, time domain transient, and then our run to time to 80 microseconds. So let's convert it to seconds, or let's just type 80 microseconds here in the simulation settings, and then click apply, okay, and then let's click OK. So we will be running our simulation. Okay, so now let's run our circuit. So as you can see, there will be a pop-up here in our desktop, which will redirect us. Now, proceeding to our analysis, we need to test or to analyze the control switch voltage as well as the voltage across our resistor load. So for our control switch voltage, let's add some traces, and then let's add the voltage. Okay, let's find it here. Let's add the voltage V pulsed plus. So as you can see, this is our output waveform for our control switch voltage, and as you can see on the waveform, we have a peak value of 5 volts for our pulsed waveform. And then, if you can still remember, we set our pulse voltage source settings with our pulse width equal to 10 microseconds. So this is the 10 microseconds here, meaning this will be the duration of our pulse width. And then we also set our period to 25 microseconds here. So if you can still remember, period is the time it takes for a waveform to complete its cycle or repeat itself, meaning this means that the switch will be on with a peak value of 5 voltage for 10 microseconds, and then will be off for this time duration until it will be able to complete its one cycle again here in our 25 microseconds period. So that's our analysis for our control switch voltage. Now let's proceed to our voltage across the load. So we will be adding our new trace, which is our voltage across the load. So it will be V2 R load here. So for us to focus on the output waveform across the resistor load, let's delete the other one. So this is the output waveform for our voltage across the R load, which will give us almost 24 volts here, and as you can see, it has a pulse width of 10 microseconds. Same with our voltage controlled switch, and then again, our period here will be 25 microseconds. Same with our control switch voltage, meaning the two pulse waveforms are in phase with each other since their period is similar as well as their pulse width. So same analogy, taking note of our almost 24 volts peak voltage here. The voltage is applied here when we had our peak value, and then it will be off here up until it reached its 25 microseconds period, wherein it will be able to repeat one cycle all over again. And this waveform process will repeat for the time duration we set on our simulation settings. So that's our part 1. Now, proceeding to our second part of our experiment number 1, we have to create another project or another circuit, but this time we will use the MOSFET IRF150 as our switch, compared to our S-break switch a while ago. And then we will add another resistor here before our MOSFET, which will have a value of 10 ohms. And we will be explaining the result later on. Now let's fix our components. So let's delete this one. So let's delete it, and then let's delete the ground on our voltage source. And then the additional wire, let's delete it as well. And then we will have the same pulse here. Okay, let's rename it V control. Okay, in accordance to our circuit. So V control, and then let's copy the resistor here. So let's rotate it. So let's rotate our resistor, and then let's place it here, connected to our voltage supply. So let's just delete the unnecessary wire connections. Okay, so let's fix our circuit here. Okay, let's delete it. Let's delete all of the component, all of the wires, and then let's connect our resistor here. Now we have to delete this wire here so that we can put our MOSFET on the circuit. Then let's choose the working MOSFET here. So I think this is it. So let's connect our IRF 150 MOSFET here. Let's press escape, and then let's connect our wires to our circuit. So we will be connecting wires. So our resistor will be here, and then let's connect our MOSFET to our DC voltage source, and then our resistor to our MOSFET, and then this part will be connected to this part, and then let's move this a little so it would fit, and then let's put a wire here on the resistor to connect it. And then don't forget that the ground here is not needed, so we have to delete it so the circuit will be functioning well. So let's rename our V pulse as V control. Enter. And then let's rename our R load as RG here, and then the value will be 10 ohms. Also, our R load will be R load, and then the ohms will be 2, and then our voltage here is 24 volts, and our V2 is 12 for the pulse voltage source, and then TD will be 0, TR is 1N, and the rest of the parameters is the same with our part 1. Of course, do not forget our ground here, so the circuit will be functioning well. So this will be our circuit for part 2. Now it's time to run our simulation. Again, you have to take note that the simulation should be same with the simulation settings we set on the part 1 of our experiment. So our run time is 80 microseconds, and our start saving data after is 0, and then our analysis type is time domain transient. Take note of that. Okay. Again, there will be a pop-up here on our screen. So we will be testing the voltage across our pulse voltage source. So let's add some trace. So the first voltage will be our voltage on our pulse voltage source, and then next one will be the voltage across our resistor connected to our gate. Okay, so before we proceed, the green or the square here on the output waveform is our voltage across our pulse voltage control source, and then the next one is the diamond or the red waveform, which is our voltage across our resistor, which is here, our resistor here, which has a 10 ohm value, which is the RG connected to our gate, to the MOSFET gate. Okay, so let's go back to our simulation, and then let's add another trace. We will be adding the trace for our voltage across our gate, across our MOSFET gate. So let's add our trace. So let's add, and then let's find for the voltage M1 across the gate. So the blue line or the blue waveform with triangle is the voltage across our MOSFET gate, and another one which we will be plotting is the voltage across our load resistor here, connected to the source of our MOSFET. So you have to remember that this part of our MOSFET is our gate. This part here is our drain, or if you can still remember the transistor in comparison to MOSFET, this is the emitter. So since we are using MOSFET, this is our drain, and then we have here our source, okay, or in a common transistor it's an emitter, okay, but since we're using MOSFET, it's our source. Now we have to plot the waveform of the voltage across our R load here, which has a 2 ohm value. So let's go to our trace section, let's add trace, and let's add the trace for our voltage across our R load with the 2 ohm value. So this yellow waveform here is the output voltage waveform for our load resistor connected to our DC voltage supply. Now to analyze, as you can see, let's first start with our voltage control, with our voltage across the gate, and with our voltage across the resistor connected to our gate. As you can see here on our circuit, the resistor connected to the gate of the MOSFET and connected to the pulse voltage also has the same value of the peak voltage on our waveform here. That is because the components are connected in series, meaning the current flowing on the resistor will be the same with the current that will be flowing on the gate before the current gets distributed to the other components or parts of the circuit. So if you will be multiplying the current, okay, the current measured on each of the node of the RG or the resistor connected to the gate, it will be the same, and if you will be multiplying it by the values, it will yield to the same voltage output result. So that's the principle behind why does the output waveforms of these three parameters are of the same value, which is almost approaching to 30 volts. So to be specific, let's put our cursor on, and then we will be measuring the peak value of the voltage of these three parameters. So based on our simulation, we have here peak voltage. It's the same for all of the three parameters. The V control, the voltage across gate, and the voltage across the resistor RG is equal to 35.540 volts. And now, explaining why does the output voltage across the resistor load, we have to measure the peak voltage of our voltage across our resistor, which is connected to the VDC. So as you can see here, the peak voltage is 23.541 volts or almost 24 volts. Why is that so? So going back to our circuit, as you can see, the resistor load here with a 2 ohm value is connected to our 24 voltage DC supply. So what comes from the 24 voltage DC source, that will be received by our resistor load here. And since this resistor load has only a minimal value of resistance, that is the reason why there is a small voltage drop across our resistor load, which is 23.41 volts, because the resistance is just 2 ohms, or technically speaking, it's just a small resistance compared to the resistance commonly used in some circuits. Now, as our summary, it is really important to take note of the three terminals of our MOSFET, which is our gate, as shown in this picture, drain, and our source. And we have two types of MOSFET, which is the N-channel MOSFET and the P-channel MOSFET. And to further explain the operation of the MOSFET, in accordance to our simulation, so we have the MOSFET operation region here, as seen on the graph. So this is the cutoff region wherein there will be no voltages that will be flowing, or let's say there will be no voltages supplied to the circuit. So going back to our waveforms, so this is our cutoff region wherein there is no supplied voltage on the circuit. And now for our another operation for our MOSFET, we have saturation here, wherein there is an exponential movement of our waveform from the zero part of our x-axis and our y-axis now having value. So here in our waveform, this is the saturation region wherein there is already a voltage supplied to our circuit. So that's the principle behind the MOSFET operation based on our experiment. Now, for our conclusion, using the ORCID Lite software, we are able to measure the value of the node voltages and understand the role of a voltage-controlled switch and the MOSFET in circuit. We also explored how voltages are related in accordance to how the components are placed in a circuitry. Moreover, a voltage-controlled switch can be completely on or off depending upon whether the input voltage is above or below the requirement for it to work. Moreover, in general, the MOSFET works as switch by controlling the voltage and current flow between the source and drain. When there is no voltage applied to the gate terminal, there will not be any current flow apart from a small amount of current due to minority charge carriers. To turn off and on a MOSFET like a switch, the minimum voltage should be met at which the MOSFET starts conducting, which is called the threshold voltage. And for our application, overall, knowledge about voltage-controlled switches and MOSFET as on and off devices connected in a circuit is helpful for power electronics applications requiring high switching speed like DC motor regulation, voltage control, and radio frequency applications. MOSFETs and switches are essential devices used in the design of many circuits ranging from a simple driver circuit to complex power rectifiers and inverters. So again, my name is Rikami S. Casabuena from ECE31, and that's the end of our experiment number 1. I hope you learned something from our vlog, and see you on our next power electronics video. God bless!